Hey everybody, last video in the rotational motion series. It'll set us up for pretty much everything we need for chapter 7. Save one thing. So again, I ended the last video drawing a disc, like maybe something. I'm going to actually redraw it on a different piece of paper here. I'm going to place this yellow piece down and draw this a little bit more clearly. So I have something circular that's rotating. Let's have a reminder that everything from now on counterclockwise is my positive rotation. I have a center of rotation of this disc, so it's a rotating disc or a spinning disc. I have two objects on it. Maybe they're specks of dust. Here's speck of dust A, and way out toward the edge, here's speck of dust B. As this disc rotates, it's going to rotate through, let's just say, something that looks pretty close to 90 degrees, just to keep the explanation easy. But if these are two people running around a track at the end of, say, a track like at a field, B has to run this whole entire path. So B's arc length is actually this right here. This is B's arc length. But B went through 90 degrees. A also went through 90 degrees, but A had this arc length. So we know that from linear distances, A is actually running a shorter distance than B, even though they're both rotating through 90 degrees. So what I know is that they're rotating through the same theta, the same number of degrees, yes, and they are spinning or rotating at same speed. They're rotating at the same angular velocity. Same angular velocity, but I know that B is running a longer path than A, so there must be some way to connect the idea of angular motion to rotational motion. Okay, so there must be some way to figure out the actual velocity. At any instant, B has a velocity vector that's like this, but A's velocity vector is going to be parallel but less, because A is going to cover a little bit less distance in every piece of time. So velocity has to be connected to angular velocity. So it's linear velocity at any second. It's speed at any second must be connected to its angular velocity. But how? How is it connected? Well, what is the difference between A and B? The big difference is A is this distance away, has radius A. How far away is B? Wow, B is all the way out there at radius B. So that must be the connection. You know from maybe being on a merry-go-round, the farther out you are, the faster you feel you're going. The farther out you are, you know you're spinning. All the people on the merry-go-round are spinning through the same number of revolutions, same number of degrees, same number of radians every minute. 2 laps a minute or 10 laps a minute or however fast the merry-go-round is going. But the further you are from that point of rotation, you feel a different speed. So that is what fits here. How far out are you? The instantaneous speed or the tangential speed, depending on what you use for a reference, is the angular velocity, so how many degrees per second you're going, how many revolutions per minute you're actually turning, but how far out are you is going to have a different speed. Similarly, if we want to know the tangential acceleration and compare that to angular acceleration, so is the object spinning and then spinning faster and faster and faster and faster and faster, or is it slowing down? Every molecule of that disc or that merry-go-round is going to be slowing down to a stop. But we know the further out you are, you feel that acceleration differently. So that again is the connection. So with the sheet that you'll be provided, you'll have a little box here and here to connect the ideas of, I'm going to circle it in red, to connect the idea of velocity to angular, or speed to angular velocity. And that speed is the radius you are out times angular velocity. And how do we connect acceleration that we feel to angular acceleration, rotational acceleration? That is, acceleration is equal to r alpha.